Welcome to Fun with Science, Engineering, and Technology. I'm Mr. Ross, and my assistants today are Richard and Michelle. And what we're going to do is, they're up in the 8th grade, and what they're doing is they're studying catastrophic events. A hard word to say. And what are catastrophic events? Do you want to tell me what you're studying?
Hurricanes and
earthquakes and volcanoes and tornadoes and all those things. All right, we're going to do some fun things, all right? Try to relate those to what they're doing in the classroom. Okay? So I have some fun toys. First of all, I have, what's that look like? Vacuum cleaner hose, right? How about that? Isn't that exciting? What? Look at it. What's down in there? Anything in there? How about that? A cotton ball. Wonder who put that in there. Now let's try it. All right. Now that's a little bit better, right? At least it does something, right? And you can go home and get your vacuum cleaner hose out. Your mother will be mad at you, and you go running around the house going. Question is, how does it do that? It's just a piece of, little springy hose. We took the cotton ball out of it. We put the cotton ball back in. Try it again. What is? Nothing. You want to venture a guess as to why it does that?
Because of the air that's going through it?
There's air going through. With the cotton ball in there, there's no air, right? Right, so nothing happens. But if I take the cotton ball out, there's air going through it. How does the air go through it?
When you twirl it?
When I twirl it. Okay, why wouldn't I? Is there air going through it now?
Yeah.
There's air in it, right?
Mm-hmm. Yeah.
But is there any air going through it?
No.
It's not making any noise, right?
No.
It's not making any sound. But why would I twirl it like this?
For the air to get out.
Why? Okay, but how does the air start going through there? It's because of the Bernoulli effect. If you, here, take this. You know the answer to this. Right? Take that piece of paper. You've done this in the classroom somewhere, right? Try it. Go across it. What happens to the paper?
It goes up.
It goes up. Right? And that's because of something called the Bernoulli effect. Same thing that makes an airplane fly. Right? And what Bernoulli said was, is you take a fluid, and air is a fluid, really, right? And the faster it moves, the less the pressure. Right? So if we blow across the top of this thing, like across the top of an airplane wing, right? And the air is going across the top of it faster up here, so the air pressure is less here than it is underneath it, because the air is not moving as fast underneath it. So what's going to happen is we've got more pressure underneath it, and it's going to lift it. Right? So that's a Bernoulli effect. You can put the paper down. All right, so now then, when I take this and I spin it like this, what happens to this end up here compared to this end down here?
Because it bends?
It bends, but as far as speed is concerned, this end is not hardly moving at all, right? Mm-hmm. This end up here is moving through the air pretty fast. So the air going across the top of it is moving pretty fast. So what about the pressure here? It's going to be lower than what it is down here. We're going to have a high pressure here and a low pressure here because of that guy Bernoulli. Okay? Same thing makes airplanes fly. So we take this, we've got low pressure here, high pressure here, and just like when you were studying the weather, you got a low pressure area and a high pressure area. What happens? You get wind, right? The wind goes from where? From the high pressure area to the low pressure area. It tries to fill up that spot. So we take this. Right? And what we're doing is we're creating what kind of pressure here?
Low.
Low?
Low.
What kind of pressure is down here?
High.
High. So the air is going to go through the tube. Can we prove that? You think we might be able to prove that? That was one reason for the little cotton ball. Right, what I want you to do, Richard, I want you to hold on to that. Right. I'm going to get it going, right? And I want you to take that piece of cotton that I have and put it in here, and let's see what happens to it. All right, let's do it this way. Where did it go?
It came out.
It went out over there somewhere. So what happened is we had some air. We just proved that there's air going in this end, and where's it coming out? Up at this end. All right, you want to try it again?
You try it this time.
All right. There we go. How about that? So listen to it very carefully now.
Faster you spin it, the more noise it makes.
The faster I spin it, the more noise it makes. But what else is about it? That's a pretty low frequency, right? It's low pitch, like my voice, low, low. Got a little bit higher, higher pitch. And even higher yet. So what is happening now is as the air goes through here, if we go real slow with it, the air's going pretty slow, right? But what it's doing is generating some sound waves in here as it goes across all these corrugated things, right? The air goes slow, we got a low frequency, a low pitch, right? The air goes faster, we get a little bit higher pitch. If it goes even faster, we get even a higher pitch, right? So we have some sound waves. Want to try it? Don't hit her. And I'm going to get away from you because I don't want to get hit either. All right, I have another fantastic toy. Let me put that one for the time being. It's a little plastic tube. It has some holes up here, right? And it has a thing on the inside that slides. What's happening? We've got some lights. It makes noise, right? I'm going to lay it down. I want you to tell me what happens to the light after I lay it down there. Well, now, why do you think it's making the noise? Why does it
Air
make
pressure?
Yeah, well, yeah, it is air pressure, right? But what makes the noise? The lights went up, right? I picked it up and the lights came back on.
The lights are making a noise?
The lights are making a noise? No. Right. What's making the noise is something like this. Have you done this, taking a ruler, right? You make a noise, right? Because the ruler is vibrating back and forth, right? And if we change the length of it, what happens to the pitch?
So
It gets, the shorter it is, the higher the pitch or the higher the frequency. Make it longer, it gets lower. So with this thing vibrating back and forth, what it's doing is squeezing the air together and causing the air to expand, squeeze together and expand. And that's what makes the noise that we see. So actually in here, in this little thing that we have on the inside of this, down in here, there's a little teeny, like this little teeny tiny ruler, right? So there's a hole there, right? So as the air passes through, what the air is doing is causing that little teeny tiny ruler, or little reed, as they call it, to vibrate, and that's what makes the noise. So, does it make any noise right now? Why not?
Because no air is going through.
There's no air going through it. So, why did I take it and I put it in here, right? And if I let go, what's going to happen to it?
No.
Well, where's it going to go?
Inside the tube.
It's going to go down here. What's making it go down here?
Air.
What's making, if you were to fall down, what's going to make you fall down?
Gravity.
Gravity. Gravity. So if I let go of this now, gravity is going to cause it to pull down. All right? And what you need to do is to put the, all right? So gravity pulled it down, right? And what we're doing is we're getting some air going through here, right? And causing that little reed to vibrate and make that noise. Let's take this up. Set it up there. Why are the lights blinking?
Because it was moving.
Okay, they were moving. Now they stopped.
Because the air pressure made it turn on.
The air pressure made it turn on, you think so? The light lit up, right? And pretty soon they're gonna stop. They stop. Right? So if I take this and I pick it up here like this, right? It didn't go on, did they? If I go like this, it didn't go on. If I go like this, it didn't go on. But if I go like that, they did. You know why that is? Because there's a little thing in here, right? Just a little tiny thing called an accelerometer. Big word, huh? Do we know anything about accelerometers? Yes, you do. Sure you do. You know everything there is to know about an accelerometer. You get in the car, you're sitting in the back seat. Right? Mom, Dad starts it up, puts it in gear, takes off. What happens to you?
Push you back.
You go back, right? She slams the brakes on, what happens to you? You go forward. You know what you are? You're an accelerometer. She goes around a turn, what happens?
You turn.
You fall over to the side, right? Go around the other turn, right? So, accelerometers work the same way. What they measure is acceleration. If you're sitting in the car, and she's out on 495 driving along, it's a nice fancy car, nice shock absorbers, right? It's all quiet. Do you feel anything as she's driving along? She's driving along at 50 mile an hour constant speed.
Pressure.
Do you feel no? But do you feel anything? Do you push back against the seat?
Yeah, push back.
You sure? Or you're sitting there, you're nice, but you're not like when she steps on the accelerator pedal, right?
Mm-hmm.
So you're just sitting there, and if you were to close your eyes, right, and it was a nice riding car, you probably wouldn't know that she was going down the road at 50 mile an hour. You probably wouldn't feel anything. It was nice and real quiet. Right? The only time that you would know if you had your eyes closed that something was happening is she slammed on the brakes. Right? And what would happen?
You go forward.
You go forward. Step on the accelerator pedal and speed up. You go back. Right? So the only thing you know is you had your eyes closed. It was a nice quiet car, nice smooth riding car, is when it changed speed. Right? Either slowed up, speeded up, or slowed down. So when it changed speed, that would be the only time that you would know that anything was happening. Or when it changed direction. But all those things are called acceleration. Right? You're speeding up is acceleration, and when you're slowing down, it's deceleration, or it's acceleration in the opposite direction, right? So what you are is you are a little accelerometer, or something that measures the acceleration when you're sitting in the car. The same thing is true here, right? There's a little thing in there that's like this. This is a plumb bulb, right? If you watch it very carefully, right now it's just sort of hanging there. It's hanging right straight down because gravity's pulling it down. But if I take and I move my hand, right, this thing is going to want to stay where it's at. It's nice and heavy, and if I quit shaking, and I move this way, if you watched it very carefully, what happened to it? It tried to stay over here, right?
Mm-hmm.
And then eventually when I stopped accelerating, it finally caught up to me, but it tried to stay there. Right? Same thing is true if I go this way with it. Right? It tried to stay over here, right? If I go this way with it, tried to stay over here. Well, inside here, there's a little tiny one of these things, right? So right now, while it's setting still, it's just sort of hanging there. If I pick that thing up and I move it, right? If I move it this way real quick, right? What's going to happen is that little accelerometer thing in there is going to move, right? And when it does, it closes an electrical switch, right? Like going over to the light switch and turning the lights off and on, right? This thing is going to trip that switch and cause those lights to go on. Right. And then there is a little timer that says, okay, just like the timer on your microwave oven or your toaster or whatever, says, okay, you've lit up long enough, right? You're back at rest, right? You're not moving, turn the lights off. Right? So that's how that all works. I take this and pick it up and right, and the reason they flash is because there's a little electronic circuit in here, little magic circuit with a motor vibrator in it. That it's either on or it's off, it's on, it's off, it's on, it's off, and it's switching back and forth, and that's what causes them to blink back and forth like that. Do you think those are little regular little light bulbs in there?
Yeah.
Like in your flashlight?
No.
No? What do you think?
No.
No. Some of the new flashlights do have these things in them, and they're called LEDs. All right? They don't have filaments in them like those light bulbs do up there, or the light bulbs in your flashlight. Right? With a little piece of wire, you know, when if you look at the light bulb real careful, when you turn it on, you can see this little piece of wire. The one in the house that burns out, the little piece of wire is burnt, right? And you shake it, you can sometimes hear it rattling around in there. These don't have these. These, what it is a little semiconductor thing, like a transistor, right? And when you put voltage to it, a little bit of electrical energy to it, it lights up. It's called an LED, light emitting diode. Right? So, what's that got to do with anything? You're doing earthquakes right now, right?
Yeah. Mm-hmm.
Okay. And earthquakes are, what happens in an earthquake?
The earth shakes.
The earth shakes, right? So if I were to set this down here now, with my little accelerometer in there, and the earth were to shake, what's going to happen to my lights?
Turn on.
They're going to turn on, right? Earth quits shaking for a while, what happens to them?
It turns off.
They turn off, right? So, did you see the movie on the earthquakes?
Yeah.
The video?
Mm-hmm.
Remember there was a little guy that was all excited because he found the airbags in your car, right? What sets them off is the car stopping real quick, right? So what do you think the device is that sets those off? Is an accelerometer, right? You want to go driving down the road, you run into a bridge or run into another car, and what happens? The acceleration changes real quick, and that accelerometer senses that change in motion and triggers an electrical circuit which pops the airbag. So, now then, same thing happens here. And what he was going to do with those little accelerometers out of the automobiles, he was going to place those up. Where was he going to do with it? He was going to place those all around the area, right? So, and monitor them all, because they were cheap. He could put out thousands of them, and he could monitor them and detect all the earthquake waves, right? The shaking of the earth, and determine where the earthquake was coming from. He collects more data. Yeah. What's that machine called that does that normally? Do you remember? It generates a graph. Did you see the thing that generated the graph? Right.
Yeah.
We have one here anyway. Okay. Very simple one. This You haven't done this in class yet, have you?
Mm-mm.
Okay. This is what this is an accelerometer. If we take, and let's leave it up off the paper for a minute. If we take and we wiggle this, move the table, what's going to happen?
That's gonna move.
That's going to move. It's just like you sitting in the car. All right, this thing is going to try to stay where it's at. Right. If we move the table this way, it's going to try to stay where it is. Right. So it vibrates back and forth because of this piece of plastic that we have up here. Right. So the fancy name for this is a seismograph. Right. And what it does is the fancy ones are going to use it to measure the amplitude of how much the earth shakes, right? And possibly what direction it's coming from. Okay, so what we're going to do is right now it's sitting there, and if we pull this piece of paper like this, what happens?
Go straight.
It makes a line. That makes a straight line, right? So let's call that the start. All right?
Mm-hmm.
Now, what I want you to do very gently is I pull the paper, I want you to bang on this side of it a little bit. Go ahead, keep going hard, a little harder. All right? Okay. So that was from this side, right? Now then, as I pull the paper, what I want you to do is bang on that side. All right. So very good. So if we go up, pull it again, and you go over there and just sort of step around the side over there and bang on that one. All right. Very good. So now let me just move it a second, and I'm going to take and pull it. Right. We got a straight line. All right. So what happened to the line when I was pounding on this side?
It didn't squiggle that much.
It didn't squiggle that much, but when I go this way, all right, I get a bigger squiggle, right?
Mm-hmm.
If I do this, I don't get as big a squiggle. Right? So if we take a look at it, right, if it's not vibrating at all, right, I got a straight line like this. This is where I banged on this end of the table, right? It's a little bitty squiggle. This bigger one is when I hit it from the side, right? This bigger one here is when I hit it from this side and I hit a little bit harder. And that's the way seismograph works, right? Of course, they spend a lot more money to build their seismographs than what we have here with these two little pieces of wood and a little piece of plastic and our pen, right? But it works basically the same way, all of them. No matter how much money they spend on them, they're still accelerometers, and they work basically the same way. So that's how they measure the strength of the earthquakes. If our table were real steady, right, and I were to bang on this side here, right, that wouldn't move at all, because what I'm doing is I'm making the wave come in this direction, and this thing shouldn't move, right? So if I bang on this side here or this side here, that if the table were real steady and didn't wobble around, they would make a straight line. Where if I banged on either side over here like this, it would make a line back and forth this way. We get that squiggly line. So we could tell basically where the earthquake was coming from. The earthquake, my seismograph was sitting here, and the earthquake happened over here somewhere, right? It shook the ground this way. My seismograph is going to make a squiggly line. If I would have my earthquake over here, right, and the waves from the earthquake come this direction, the seismograph wouldn't record it. It would be a straight line. So I could tell basically whether it's over here, or maybe it's over there. So I could tell where they're at. Okay, so what's the thing that turns the light on? It's it measures acceleration. It's an accelerometer. right? What's that thing? That's a seismograph, but what is it really? It's an accelerometer, right? Because right now it's setting still, and this is standing still. But if I take and I hit it here, right? This pin tries to stay where it was, just like when you're riding in a car, right? You try to stay where you're at, right? As you accelerate, right? You either speed up, slow down, make a left or right turn, and you try to stay there. And we could hook you up. We could put you in a car, right? And give you a pen, a piece of paper, and if we had an earthquake, you could be our seismograph, right? Or if we hang you from a string like this, okay, and give you a pin, right? And this was fastened to the earth somewhere, and the earth started shaking, right? We could make you a seismograph, right? So you knew what an accelerometer was all along. You were just trying to confuse me, right? So what about this? Why does it make the noise?
The air goes through there.
The air going up through here, right? And why does the air go up through here? Because
there's high pressure.
Because there's higher pressure here than there is up here, right? This is low pressure. And why is this low pressure up here? Because the air is moving across the end of the tube, right? And it's not moving down here. So that guy Bernoulli, right? He keeps messing this up all the time, and he says that, right, if the air is moving faster, the pressure is lower. Same thing that makes airplanes fly. The faster I go, the faster the greater the difference in the air pressure between the two, and the more wind, the faster the air is going to flow through here, which gives me a higher pitch or a higher frequency. If I can do it real slow, right, I get a low frequency. All right. So what we have then is this has what in it? What made the lights come on? An accelerometer, right? Which sensed the motion, right, when I picked it up, right? If I put it in here and go down through the tube, I get a little noise out of it, which, because when it falls down here, it's pushing air through this piece here. When it goes this way, the air is coming up through this way, right? And there's a little vibrating reed in there, like this ruler, right, that makes the noise for me. And if I leave it lay there for a while, light went out. Why? Because the timer said, hey, it's not being accelerated anymore, it's not moving, and shut off the light. And those little lights in there are called what? LEDs. What's LED stand for? Light emitting diode. Okay, so, and again, a little piece of fuzz, just to prove that the air is really flowing through here. Let me go it this way. Right, go up. Okay, so this part here, acts like an accelerometer again. If the Earth moves this way, right, that wants to stay where it's at, right, and it would draw a line off in this direction because the Earth is going to move the base. Right, if it moves this way, they're going to draw a line over that. And how far it moves depends on how much acceleration we get, how fast the Earth starts to move. If the Earth were to move this way, right, this thing is pretty stiff in this direction, right, so it's not going to vibrate, and we get a straight line. So but if we look at our little accelerometer there, we can tell whether the earthquake was over here, whether it was over there, whether it was in this direction, or whether it was in that direction. If we use a couple, three of them, we can probably pinpoint exactly where the earthquake earthquake took place. Okay, so that's it for today. And what causes this?
Air pressure.
Air pressure. Difference in air pressure. Same thing that makes airplanes fly. Same difference.